Let's begin. Welcome again. I want to be done with linear solvers today, and there's a extra credit homework that I published today. It's on linear solvers, specifically for iterative solvers. So you're welcome to do that. You'll get extra credit on homework 4. So the grade on that extra credit assignment is 0, because the credit you will get up to 50 points goes on homework 4. Okay? So an opportunity to get some more points.
Can you get like 150?
Yes, yes. That's called extra credit. Yep. And so that's a good opportunity to make up for lost work, and I'll try to do that going forward. There's not much opportunity, but maybe this year there is, because we're staggering things a little bit differently than previous years. Last week we left off looking at our first iterative solver, which was the Jacobi iterative solver, and a lot of you were squinting at me and confused, like, how did you do this iteration, etc. But eventually, when you did the work by hand, it kind of clicked. We start with an initial guess, we repeat the recipe, and we use the improved guess and plug it back in and keep going and going. So we introduced you to the concept of iteration, which will be very important for nonlinear solvers. But before we start on nonlinear solvers, there's a few things we need to do with the iterative solvers. And where we left off last time, when we implemented our code, if you remember, we put a maximum number of iterations. Like, how many times do we have to keep refining our initial guess until we get a solution? And we put in 100 iterations or 1,000 iterations. Now, for that particular example, for that particular problem, you will see in the first few iterations, we had like these 3 unknowns, x1 and x2 and x3, that we're solving for. And the true answer was 0.9 and 3 and 2.3, if you remember. But then I'm summarizing here in this table the values of these unknowns as we solve them, because each iteration is going to improve the value. So we started with 1, 1, 1, and then 1.6, they became 1.6, 3, 2.25. They oscillated a little bit, but then you'll notice that after a few iterations, in this case, like at iteration 10, we start converging to an answer. We no longer oscillate that much. We start getting to a point where the answers do not change anymore. So if you look at the difference between 10 iterations, 20 iterations, 25, 30, all the way to 40, like, these numbers are not changing. And when they're changing on like the 7th or 8th significant figure. So that's a tolerance of 10 to the minus 8. And then that begs the question, like, okay, if we could have solved this problem with 10 iterations, but we asked it to do 100 iterations, isn't that a waste of resources? For this problem, who cares? But again, this is only a small piece of a bigger puzzle, usually. And if you end up wasting time on this small piece, incurring extra cost, that is going to translate to the bigger problem. Like these iterative solvers, for example, we use them when we are solving fluid flow problems, like the air moving in this room. And to move the air in the room, I have to start moving it slowly, one little increment at a time, from the air vents all the way across the room. That will take millions of steps. And in each step, we're using an iterative solver. And if in each step my iterative solver is doing more iterations than necessary, multiply that by 1 billion or 1 million time steps or 100 million time steps, then that could result in weeks of additional computational time that is useless, because we're not gaining any more information here. Like, after you hit 25 iterations in this case, there's no more new information that is useful anymore. Okay? So that leads us to the idea of when do we stop iterating? And your colleague last week said, essentially, we use the relative approximate error. Okay? Just exactly like we did when we did the Taylor series. We kept adding terms until the answer didn't change much anymore, or until the change in the answer was less than a given tolerance. In other words, your computer cannot do any better on this particular problem. And that's called the relative approximate error. new approximation minus previous approximation over the new approximation less than a tolerance. So we can use that exactly here. Okay? So we can take the difference between the new iteration and the previous iteration and divide it by the new iteration to get a sense of the error committed in each variable. And so if you do that for each one of those variables, x1, x2, x3, remember each one, it's like we're adding terms to it or we're correcting it until it no longer changes. And then you measure, you take the relative approximate error, so difference between new iteration minus previous iteration over the new iteration absolute value, and you start seeing how the error is changing. But the problem here is that we don't have a single variable, like in the Taylor series, a single result. Here we have 3 results. In the homework assignment, you're going to have 1,000 results because you're going to be solving for the temperature distribution. In large systems, you could have 1,000,000 results because you're solving for 1,000,000 unknowns. Each one of those unknowns is being iterated and converged, and it has its own relative approximate error. That's why I have, in this problem, where I have 3 unknowns, I have 3 columns for the error. Okay, the first column, you see the error going from 10 to the minus 1, 10 to the minus 4, 10 to the minus 7. But the other one looks like it's converging faster. So after 30 iterations, the relative approximate error in the first variable is 10 to the minus 7, but in the second variable is 10 to the minus 9. Same for the third variable, right? Now this poses an interesting question, like which one should you pick to say that the whole system has converged? Your colleague also said last week that, oh, we're just going to pick the worst one. So pick the variable that has the worst error and keep driving that to whatever tolerance you want. So what that means, say your tolerance is 10 to the minus 9, and I'm looking at these, looks like this one has the slowest convergence. So I'm going to keep iterating until this one reaches 10 to the minus 9. Or until the worst error across all of those reaches 10 to the minus 9. So we hit here, we're good to go. Although these guys are smaller, but doesn't matter. The worst one was 10 to the minus 9, we're good to go. That's a legitimate way to measure this, okay? Absolutely legitimate, okay? If you remember your exam 0, this is called the L infinity norm, okay, which I will discuss next. Now, together, E1, E2, and E3, all of these errors, at each iteration, remember you're doing a relative approximate error, but at each iteration you have 3 errors, or however many unknowns you have, you're going to have an array or a vector of errors. Okay? Now together, if you look at E1, E2, and E3, you can think of them as an error vector, a vector in the error space. Okay? And the minute you make that jump, you can now start using vector theory to calculate some measure of that total error. So I have 3 errors here. I could pick the worst one, which means I'm picking the maximum one. Or I could say, what if I take like a Pythagorean norm or some average of them, right? So, but that's it. That's what we're going to do. But if you think of them as a vector, that gives you a few more tools, which brings us back to vector norms, which we discussed in for exam 0. Now we're going to come back to them because they're very, very useful in determining convergence. Okay? So vector norms are essentially just a measure, a collective measure of a sequence of points or values. Now, we loosely call an array a vector. It's technically not a vector because true vectors, they're pseudo-vectors. What we call them, true vectors have to obey certain basis and rotation rules. But for the sake of the argument, just humor me, you can think of an array as a vector in n-dimensional space. Doesn't have to have 3 components. Could have 1,000,000 components. It's still a vector in a 1,000,000 component space, okay? But the point is that all of those points together, if you use vector theory, you can get a measure of the average value of those points. From vector norm theory, you can define a bunch of norms. They're just, again, just a measure. What do I mean by a measure? Like how long it is. How long is the vector? Literally, that's what the measure is. You have the standard Pythagorean norm, which is the A2 norm, the second one here in the middle. That's called the L2 norm. That's when you have a square or a rectangle and you want to measure the diagonal. You say the length of the diagonal is equal or the length of the diagonal squared, is equal to a squared plus b squared. That diagonal, if it were in n-dimensional space, it would be diagonal squared equal a squared plus b squared plus c squared plus d squared, etc. Okay? That's a general Pythagorean norm. It's a norm called Pythagorean norm, or the L2 norm. And it's defined by this as the square root of the sum of all the components squared. So square root of the sum of a squared plus b squared plus c squared plus d squared, etc. But you also have other norms. There's the L1 norm, which says simply just take the sum of all of the numbers in the array, or the vectors. You can average them, divide by the number, gives you another norm. Okay, that's one measure. Another measure, which what we discussed last Thursday, is take the worst case, takes the worst value as a representative of that vector. That's called the L infinity norm. Why? Because it's taking the maximum value of all the components. Okay? You're familiar with norms. You did well on exam 0, so I expect you to know those. Now, in Python, you can simply compute a norm on an array, on a NumPy array, using numpy.linalgebra.norm. So now we have so many tools under our tool belt, matplotlib, numpy.array, linalgebra solve, linalgebra inverse. Here's another one called norm. You simply take a NumPy array in the first argument, and the second argument you tell it which norm you want, L1, L2, or L infinity. You actually have L3, L4, L5, whatever norm you want. Okay? But the ones that are commonly used in practice are either the L2 or the L infinity norm. The L infinity is very restrictive, okay, because it's always taking the worst case scenario, and oftentimes, what if you never converge to that point? So sometimes you have a stubborn variable, like I said last time, and it doesn't want to converge below your tolerance, so you get stuck. The L2 norm is a little bit more forgiving because it balances things out. If most of the variables in your system have converged to 10 to the minus 9, and only one is still at 10 to the minus 7, who cares about that? Okay, let's just take the aggregate and move on, right? So the L2 norm is very nice and kind of balances everything out, okay? So we can simply compute the norm of the error vector and then stop iterating when that error is below our tolerance. So for example, now I'm going to go back to this problem where we had x1, x2, x3. Now we have error 1, error 2, error 3, or errors committed in each of those variables, the relative approximate error. And if I take the L2 norm, which is the sum of the square root of each one of those squared, okay, so square root of the sum, so you take the sum of this squared plus this squared plus this squared, you take the square root, it gives you this one, all right? So now you see how it kind of balances things out, okay? And then you can say that, okay, this is a single number that I can use to assess my error, rather than dealing with 3 or 100 numbers or 1,000,000 numbers. It's just one number, and if that number is less than your tolerance, you stop, okay? And that's how we assess convergence, regardless of iteration count, okay? So in practice, what you would do is go by tolerance. You don't want to keep iterating for nothing, but you also should put a maximum cap on iteration count. Because what if, let's say, your tolerance is 10 to the minus 7, and you never hit 10 to the minus 7? What, you keep iterating? No. You say, okay, I'm going to hit 10 to the minus 7, but if I cannot do it in 25 iterations, I'm going to call it quits, okay, and move on. So that's what you do in practice. So you need both a tolerance and a maximum iteration count. Okay, so this is how we compute an aggregate error, okay? And this is only one type of error, though, the relative approximate error. I really like the relative approximate error. It's convenient and nice. However, that's not the only way to compute these errors, okay? There are other error measures, and specifically, what's nice about this is that, well, we have the linear system already. So I kind of have a surrogate for the solution. So why not take my numerical solution and plug it back into the system and see if indeed ax equal b, right? Because I have a, it's given, I have b, and I'm trying to compute x. If I take x and plug it into ax equal b, into ax, does it equal b? So in a way, you have also a sense of true error that you can measure, okay, with these linear systems. So there are different error measures. You have the absolute error measure, which is simply saying exactly what I said right now. If you take the whatever iteration you have, take your solution, plug it back into the system, and take the difference with B, that gives you a true error. That's going to give you a true error, right? If I have 2x equal 3, and I give you, and I say x is 1, you put 1 in the system, 2 times 1 is not equal 3, but you can measure an error, right? Then I give you 1.2. 2 times 1.2, is that equal to 3? How far away is it from 3? So you have a sense of true error, which is really great, and that only happens with linear equations and nonlinear equations, actually. Or, if you have the exact solution, you can measure the error between the kth iteration and the exact solution. This is only for verification cases. So you implement a new solver in your code. You build a system that you solve by hand or solve with another method, and then you compare, or you use an A-inverse method, for example, a direct solver, and then you compare with that just to double check that your solver is working correctly. Okay, so that's one other way to measure error. But in practice, you don't have the exact answer. So, that's not going to be very practical. Or you can do the approximate error, not relative, just do an approximate error. Current iteration minus previous iteration. Now, the two vertical bars, they represent the norm. So essentially, that's one, it takes that entire array and makes it into a single number. Okay? This should be clear. This is an array, and this is an array of points. K is simply the iteration count. It's not a power. It's not x to the k. This is the kth iteration. And the two vertical bars are the norm. I really like relative errors, though, and you can do this, take these guys up there and turn them into relative errors. For the true one, you divide by the right-hand side to kind of measure the weight of how important that error, how big the error is. Or you can do the relative approximate error. This is by far my favorite. Okay, I always try to use this one. We will use this one in the next example, probably just to show you that how to implement it. But I really like this one in practice because it tells me my computer how good is it going to solve the system. Okay, not how good it's going to solve it in general, because there are limitations on my computer chip and how well it's going to do. And that's usually the bottleneck. Now you iterate until your error is less than a certain tolerance that you specify. Okay? Now when writing an iterative solver, it doesn't matter which error measure you pick. Usually these are very consistent with each other. They're off by a few iterations. So whichever one you pick, you're going to be just fine. You're not going to lose a lot of iteration count, doing more iterations for nothing. They are very consistent with each other, thankfully. I think it's a feature of nature that these linear systems, however you measure the error, they're going to be consistent with each other. But be clear what your code is doing. Is it using a relative or an absolute error? And then pass, because you're going to choose your tolerance based on that. Relative errors are going to be almost of order 1. Absolute errors are going to could scale with the temperature of the sun if you're solving radiation problems or something in outer space, right? So be cognizant of that, like what you provide to the user so that they choose their error accordingly. I'm going to give you the tolerances in these right now because you're going to need some experience understanding these systems. But eventually, in the area you're working in, you're going to get an idea that I'm always solving temperatures on space stations in outer space. And I have this range of temperatures. My error tolerances are going to be in the hundreds, maybe, right? Because an error in 100 for a temperature that's 10,000 kelvins, it's insignificant, right? So then your tolerance could be 1% or 10%, right, for that problem, right? For other problems, your tolerance might need to be 0.1%. Okay? So I'll give you the tolerances in the problems we're doing here, but as you start learning more about physics, you keep that in mind, that the error tolerance that you're providing for the linear solver needs to be consistent with the system you're solving. Okay. So, yep, this is code and stuff. So let's go back and maybe implement this together in Python. By the way, I have a cool new recording gig. I feel like I'm at a TED Talk, so I have this new thing. The last lecture, the audio was horrible. And I always tell you, like, don't record me in class because I provide high quality audio in my lectures. The last lecture, it was very noisy and bad. So I stopped by Surplus this morning and I found this great thing. And it was like pennies on the dollar, so I bought it. And trying it today, it looks like it's going to be good quality. It's going to do a good job. So we'll see after today's lecture. But let's grab our notebooks. Pick the one from, what is it? From last week. All right, window. Okay. Okay. So that was our Jacobi code for this little system of equations, or in general, really. All right, so I'm going to take it again and augment it a little bit. So I'm going to copy and paste here. And I'm going to call it Jacobi 2, because it's a very creative name. And I'm going to keep A, B, and guesses. And I'm going to add a tolerance to it. So I'm going to pass a tolerance option so that we can stop iterating before we hit max iterations necessarily. And I'm also going to keep max iteration, the number of max iterations, because, well, apparently you don't remember what we did. So let me remind you. So last time, we implemented a Jacobi solver that takes in a coefficient matrix, right-hand side, bunch of initial guesses, and a maximum number of iterations. And last time, we iterated up to max iter. So if we put 10, it's going to do 10 iterations. If we put 100, it has to do 100 iterations. But as we saw in the slides, we don't have to do 100 iterations. We could get by doing maybe 20 iterations, right? So now we're going to implement a tolerance feature. So I copied and pasted this here and added a tolerance option. I'm going to keep max iter because, just like I said, I want to cap the number of iterations. If the solver doesn't achieve my desired tolerance, I don't want it to keep looping forever. I still want it to stop at some point. So we're going to put a max iter option, and I'm going to default it to a value so that it's an optional argument for the user. You've seen many routines we use in Python. We didn't have to supply all the arguments. Like matplotlib, the minimum set of arguments is x and y, right? You're plotting y versus x. But there's a ton of other options that we never provided, and it was just fine, because Python defaults those to some standard values. So I'm going to do the same here. A is going to be required, B is going to be required, the guesses are going to be required, and a tolerance is going to be required, but I want max iteration to be optional, because I'm going to hard code maybe 100 iterations by default. Okay? So I'm going to say my Jacobi solver will try to solve down to your tolerance with a maximum of 100 iterations. If it needs more, it's just going to stop at 100 iterations. So the way you do this, you simply, in the argument, you say max iter is equal to 100. Okay? So now I can call Jacobi without providing max iter. Internally, it's going to it's going to know that max iter is always 100. You can still provide the option if you want 50 or 1,000 maximum iterations. It will take it. But if you don't provide max iterations, it's just going to be fine. Okay? All right, so now we need to add the tolerance here, the tolerance issue. So I need to say something like, while my error is less than my tolerance, and k is less than max iteration. Okay? So that's, in English, what I want to do. So this is saying while, or as long as my error is less than tolerance and my number of iterations is less than maximum iterations, keep doing your thing. Once any one of those is violated, get out of the loop. It will automatically get out of the loop. Okay, so tolerance is given to us through the argument. It's coming in to the routine. We need to measure an error, okay? So here's how I'm going to do that. Let's go back to the slides. Let's see which error we want to pick. Window. So for this, I'm going to pick this one because it seems the most ominous and the scariest one, b minus ax. So that's just simply the linear system itself. We have a, we have x, and we have b. I'm just going to do this operation and put it in a norm. Okay, so let's do this. So my error is going to be, define it here. Error will be, that's the initial error, b minus a at guesses, right? Now remember, guesses is going to be my xk, the kth iteration. It's going to start coming with whatever we came in from here, and then I'm going to put this in here as well as we keep computing it. Okay? So we can do this. For some people, the at symbol does not work. So another way of doing this, again, one more tool, instead of putting the at, you can do dot. So that's the dot product between a matrix and the vector. Don't ask me why they called it dot, but it does the matrix vector product. So a times x guess is going to be a times x guess, it's going to turn into a vector. So, and it will be of the same size as b. Now, what is the answer right now? Is this a scalar or an array? It's either scalar or array. Why? And why? Why is it a scalar? What is b? It's going to be an array. This is n by n matrix times an n by 1 vector of solutions. It's going to be an n by 1 vector, and this is an n by 1 vector. Okay? So now we need to convert it into a single number. This is the pointwise error in each variable. So these are the columns in the table that I showed you in each one. Now if I take the norm, it will make it a single number. So np.linalgebra.norm, and I'm going to take the L2 norm. So now it converts b minus a dot x guess, which is an array, is going to convert it into a Pythagorean norm, which is the square root of the sum squared of each entry. So now that gives me a measure of the error, okay? Now, I needed this error because I went into the loop, but inside the loop, I'm recomputing my guesses, right? So I need to copy this and put it inside the loop as well, so that I keep updating my error. Because now I go in here, I go into the while loop, this is the initial error. It's going to be definitely less, it's going to be definitely greater than tolerance. So this is going to check, and so, well, it's not going to be met. This condition is not going to be met. Neither is this condition, so we're going to go in. We're going to do our new solution, update the guesses. We need to compute the new error. And then once I'm done with the loop, it goes back here and it says, oh, is my error less than tolerance? If not, continue doing until we hit our tolerance. Okay? And that should just do it. Okay, so now I also want to return the number of iterations. Okay, actually, let me see if I can. Okay, so let me do this. Let's do some diagnostics. So what I want to do is print the solution. So I'm going to print my iteration counter, k, and I'm going to put a tab here, and then print my solution. And then I'm going to print my error. Okay, error. And that's going to be a single value for the error. Okay, and what I'm going to add here is print iteration, and then \t, and then x1, x2, x3, then another tab, and then error, and then a new line. So what I'm doing here, I'm putting a header for what I want to print, and then in the first column, I'm printing the iteration number, and then taking a tab, space, and then my entire solution, which is going to be x1, x2, x3, so 3 numbers, and then the error associated with that iteration. Okay, so then if I call my, if we go back here, this was our initial array, and we printed the solution. Now I'm going to call, so again, I'm going to take this, and I'm going to call Jacobi 2, but Jacobi 2 now takes a tolerance. So that's the guess, and then the tolerance, let's say we want the tolerance to be 10 to the minus 2, okay? And then if you run it, it doesn't do anything, okay? Okay. Did I define this? Okay. Let's do 10 to the minus 4. It's doing nothing. So I probably have an issue over here. Print error. Let me see. While, sorry, I made a big mistake here. While error is greater than tolerance. Oh my goodness. See what happened? So as long as error is greater than tolerance, then keep doing your thing, okay? So we never entered that loop. That's why. So, but you see what I did? I went back and put a diagnostic over here, because my thinking was like, what if the error as I'm going into the system is smaller than the tolerance? But that doesn't make sense. So my error was 8.3, which is definitely larger than tolerance. And then I immediately was able to see my mistake here, that this should have been greater than tolerance. So as long as error is greater than tolerance, then do the loop, okay? So let's come back here. All right, so now we have an answer, okay? So we initially come in, the first iteration is going to give us 1.63, 2.25, and the absolute error norm is 3.9, and then we do another iteration, and then it stopped at 10 once we hit 10 to the minus 2. Okay, you want more tolerance? Okay, let's do that. We can go to 10 to the minus 4. So probably going to take more iterations. Indeed, it took 18 iterations to get us to at least 10 to the minus 4. Okay, but it's going to cap it at 100, regardless of what you set the tolerance to. So let's say we cap it manually. We say max iter is equal to 10. Then it's going to stop at 10 iterations, 0 to 9, that's 10 iterations, right? The error is almost 10 to the minus 2. It's not 10 to the minus 4, but at least it's not, didn't go into doing more iterations than we desire. So your homework assignment is going to take this code, whatever one we did in class. There's a couple of codes on Canvas that you're welcome to use, also mentioned in the extra credit assignment. We're going to take this method and apply it to the heat transfer problem that you did in homework 4. So instead of solving it with the direct method, you're going to solve it with Jacobi and another method that I'm going to discuss next. Okay, and then you're going to compare the iterations and convergence properties of each one of those. Okay? All right. A lot of coding and kind of thinking about things, and I get it. You know, we have to pull you up, you know, out of your comfort zone. Okay, these are not easy things, but trust me, they're going to be the least of your concerns. You know, if you think this is hard in year 2, you have no idea what's coming at you next year. Okay, it's the cognitive awakening. And then it gets easier by year 4 because you're like, I get it now, okay? So my advice to you is go spend time on this. I know I'm not the only course, this is not the only course that you're taking. I know you have other midterms and other stuff, but this is as important, if not more important than anything else. You know it. You're going to go into the field. You need to know how to code. You need to know how to talk to computers. You need to know how to deal with data, okay? And that's going to be like, oh yeah, you should know how to do that. It's not even a skill that is an advantage anymore. It's like, yeah, you need to know that. It's like writing. That's the world we're in. Okay, that we ask for it. We want more technology, but like, yeah, we better know how to communicate with technology more effectively, right? Okay, so try it with ChatGPT. Let's see what it does for you, but you better understand what it's doing, okay? And if you don't understand what GPT is doing for you, it can solve this problem. Fine, it can give you a code. But it's your responsibility as an engineer, as an engineering scientist, as a consultant, to know what your codes are doing. Because if it makes a mess and you don't understand what the code that you've used is doing, then that's going to be on you, okay? And I've made my mistakes with GPT. I was doing, and I use it a lot it helps me a lot sort through like big documents, summarize things, etc. And it makes some of the dumbest mistakes. It was off by a factor of 1,000 in an analysis I was doing. And I'm like, I looked at the numbers, like just doesn't make sense. Thankfully, it did most of the work for me, but then I went back and I was like, you're off by a factor of 1,000. Repeat and it's like, my apologies, I made a mistake converting from millimeter to meter or something like that. It was off by a factor of 1,000, and it redid it. So, you are in control. You need to be in control of AI. That puts you in a good position, actually. So if you know this stuff, because this stuff is what built those AI tools, right? Now they're going to start building themselves, obviously, but they're going to get dumber probably. And so, if you know how they work on the inside, that is going to be your advantage as you look for the next 10 years in your career and being a prompt engineer, and all of that stuff. So there's still value in all of this, okay? So it's hard. My advice to you, could have led with that and just be done with the pontification or the lecture, is just go try it again at home today, okay, tomorrow, as soon as possible. Go do it again. One time is enough to anchor it in your mind, or if it doesn't sink in your mind, then you have a question and you ask us the question and we'll help you anchor it in your mind. That's all there is to it. Instead of waiting a month from now and saying, oh crap, there's this and there's that, there's the tolerance and there's the error norm and the vector norm and the arrays and what are the differences, what's a matrix, what's a number, right? You're going to be in that panic and you're going to feel helpless. Like, where do I start? You start today, you go back and revisit every point we made, and if one line didn't make sense, you send us a question and we'll help you fill in the gaps, okay? I hope you take that into consideration. All right, so let's come back to this, and we'll be done. I have one more iterative solver, and lo and behold, there's like two names in math and science, Euler and Gauss. I'm a big fan of Euler. I really kind of big fan of Euler. I have nothing against Gauss, but it's like, his work doesn't impress me much, but it's very I could never even touch his shoelace in the quality of like what he's done, but Euler is like everywhere. Anyway, so the next algorithm is called the Gauss-Seidel iterative solver. Okay, so one observation with the Jacobi iterative solver, which I know you all revisited and studied and you remember everything about it. If you notice with the Gauss-Seidel, we're solving equation 1 for variable 1, equation 2 for variable 2, equation 3 for variable 3, and so on. But the guesses we use for all the other unknowns when we move everything to the right-hand side, they're the old guesses from the previous iteration. In other words, the new iteration is only a function of values from the previous iteration. Then one asks, well, I solve for equation 1 for variable 1, and if I go to equation 2 and variable 1 shows up, why do I have to use the old value? Why don't I use the value that I just computed? Right? Because we just started solving equation 1 for variable 1. We put all old guesses on the right. Then we went to equation 2, variable 2, and it so happens that variable 1 showed up also on the right-hand side because they're all function of each other. Jacobi says use only the previous values. But we say, why not use the one that I just computed? Do you think it's going to affect convergence? Kind of makes sense, right? We have new information. We have a new updated guess for x1. So why not use it in x2? Then now you have x1 and x2. You go to x3. Like, why not use those instead of the old values? You do that, you cut your number of iterations by half. Just this little thing, you cut it by half. You go from 100 iterations to 50. Just that little thing, thinking differently about it. Okay? So that's called the Gauss-Seidel iterative solver. And the way I like to write it is, if you think of the Jacobi formula, it was this guy. The new value for variable I at k plus 1 iteration is only a function of old values at k, right? There's xik, xjk. Okay? With Gauss-Seidel, what we say, we move from this to, instead of doing k or whatever, we say recent. Whatever recent information you have, use that recent information. Because some of them, you have new information, like x1, or you're at variable 5. You have new information for 1, 2, 3, 4, but 5, 6, 7, 8, 9, that's old information. So use the most recent where you can. That's all there is. Use the most recent information when you can. Programmatically, what you do, you just overwrite the variable. So I'm not going to go through the coding exercise for that. The code is on Canvas, and it's explained in your homework. You refer to it if you want to dig into that. You really don't have to dig into it, but what you need to take out of this is the concept that with Gauss-Seidel, we are using the most recent information instead of the old iteration information. Okay? So Jacobi is only using old info. No, I'm not going to allow you to use the new updated values. Gauss-Seidel said, no, no, no. We're going to use the new most updated value. And doing just that accelerates your convergence. Okay? Makes you converge faster. And you will see this in your extra homework credit. Okay? So if we were to do this, I'll give you the formula here. So this is Gauss-Seidel iteration, and shows you kind of, you run through this if you want to do it. I don't think there's a need to do that, but showing the values, you will see that they converge. For most problems, it takes about half of the iteration count to achieve the same tolerance as the Jacobi method. So if we were to run the same use Gauss-Seidel versus Jacobi on the same problem we did, okay, we'll get twice the convergence. The code is on Canvas for Gauss-Seidel. Just use that to solve. Again, we're using these to solve the physics problem. So that's what's so hard about this class, because you need to learn the tools to solve the physics. You still have to solve the physics problem. So in the extra credit, I really advise you to give it a try, okay? Because iterative solvers are kind of, a little bit of an advanced topic, but I'd like you to at least try to flirt with them. Just like try to use them, okay? So try your hand at the homework credit, at the extra credit for homework 4, and with that, I'm not going to do this activity. The rest of these slides are additional material. I know many of you have been asking some questions that are outside of this universe, and so I'd like to provide you with some additional material. It's up to you. You want to browse through them, you're welcome. There's a lot of methods. There's the method called successive overrelaxation that even takes Gauss-Seidel and cuts it by even more than half, makes it even faster. And there's a lot of other material on storage, tri-diagonal matrix algorithm, algorithmic complexity and stuff, and a bunch of other things here. Okay, sparse matrix storage, advanced solvers, you might not need this now, but in 4 years, you're doing your senior project and you choose to do something with data analysis, remember these slides, or come and talk to me and I'll point you to those slides, okay?